Okay, we're live. So welcome back after the midterm. It appears we only have 5 classes left, which feels kind of crazy. I guess a couple of announcements, like the last 2 lectures I mentioned at the beginning of the course that I might be away. So I'm going to be away for a conference. So I'm going to get one of the TAs to just project the video up, and you can still come to class if you want. It'll still be at the same time, and I'll record it. It'll just be from a hotel room. So yeah, those are the last 2 lectures. They'll be on like these large language models and a review of the course stuff. And then I guess you have 2 more assignments. The next assignment gets released this Friday, and it's going to be on content we covered today and on Tuesday. And then the last one, so it's going to be a programming assignment. And then the last assignment will be released on next Friday, and it's one of the multiple choice style assignments. And that is the end of content for this course. We'll have the final exam, and it's on December 18th, which is like a long time after courses I've done. I think it's like one of the last exams for the semester, which is unfortunate, but I guess you have a lot of time to study. And then marks for this midterm, I handed the Scantrons off to get marked today, so I guess they should be back later today or tomorrow, and then I'll release the marks at some point on the weekend. Okay, I think that's all the announcements and admin things. So what do we have left to cover? So we have 4 topics left in some sense, maybe 3 kind of. So we're going to focus on classification for this and next class, and that's what the next programming assignment is on. So notice we've been doing regression all the time, and now that we've built these tools and stuff, we'll see that we're just going to basically apply the strategies you already know for designing a learner for this classification setting, and just kind of see what we end up getting as essentially the gradient steps for our gradient descent algorithm style. And we're going to break up classification into binary classification, which has 2 labels, 0 or 1, or true or false. And then we're going to do multi-class classification with more classes, any finite number of classes on next Tuesday. And then what will be left after that is to do a class on neural networks, which is just another function class. And we're just going to basically study how this function class looks like. So we've studied like these polynomials and stuff up to now. And now we're just going to study something that's not a polynomial, that's called a neural network. It's just a special function. And then the final class will be a little bit on, well, I guess not the final, but the final class before the exam review class will be on like language models, I guess. And it's just like to see how, what like all this large language models stuff that's going on right now, how it's, I guess, related to everything we learned, which you will see is, it fits in very nicely. It'll just be like a multi-class classification problem where you're trying to predict what is the correct class, but now it's a next word. And your function class is just a big neural network, and that's it. And then they really do just run like something like this regularized empirical risk minimization with all sorts of bells and whistles on how you initialize and how you do step sizes and so on, but then the idea is the same. Okay, so that's an overview of what's left. And so I guess now let's spend today and Tuesday covering this whole classification business. So let me remind you what classification is as compared to regression. The difference is in the type of labels we have. And in particular, the type of labels don't have some sort of like ordered structure, so I can't really compare one label to another and say one's closer than another one is to something. So for instance, you might have like, I guess here I go with the types of wine example. Oh, and these notes I posted, there's a couple like just plots and stuff that will save me time not to draw in class. Otherwise, I will write out most of the notes in class. And yeah, so an example of these like unordered kind of labels is usually things that are just like, I guess as the English word labels describes, as like labels for things. So like here's 3 different wine types. This Barolo, Grignolino, and Barbera. Or like another classic example is when you have to label pictures. You have a bunch of pictures. Those are your X, like your features are your pictures. And then the labels are just like, is this a cat? Is this a dog? Is this an elephant? Is this a unicorn? And then it's unclear how you would relate, like, is a cat closer to a dog than a horse is to a dog? I don't know. And so for that reason, maybe the natural loss to use here, which is a measurement, right, of how close is one label to another is just the 0-1 loss. And that's what's going to differ in this classification setting, is we'd really like to use the 0-1 loss, which is telling us that if I have some label y hat that I predicted, right? If I predict something and then I compare it to some like true y, then I will only get 0 loss if it's correct, if it's the right label, and otherwise I just suffer a loss of 1. So anything that's wrong, I get a loss of 1. Otherwise, it's a loss of 0. That should make sense. And if you plot the 0-1 loss for maybe like 3 classes like above, and I guess this is a good point to mention, where we're going to just start calling these classes instead of by the words. We're going to map them to numbers 0, 1, 2, up to however many classes there are. So if there's 3 classes, then you have 0, 1, 3 minus 1, which is 2. Okay. And the reason why is because obviously we're going to want to do mathematical operations on some of these numbers. Okay. And so if you like plot this loss function where you fix, let's say, the label, let's say the true label to 1. So imagine the true label is like this Grignolino wine. Well, then, if you plot it as a function of your prediction y, that's your x-axis, well, you can see you get a loss of 1, which is bad. If you predict something other than 1, right? If you predict 0 or 2. And if you predict a 1, you get a loss of 0. And if you have multiple classes, then everything else would also get a loss of 1, except for the correct prediction. Okay, and if we just keep going forward with our story of what we have done before, well, then we'd have this like, you can write out what the risk is for this loss function. And you can also write out the empirical risk, which was this quantity, which you would just take the sample mean of this loss. And then you would go ahead and try to apply ERM, and you would try to minimize this quantity. And you would like plug in a function f here that comes from some function class. And then you would probably try to take some derivatives or something. And then you would run into some problems. Because if you remember, this whole like taking derivatives business is a good idea if we have like a continuous function that we need to optimize over. And unfortunately, this function, even just before we even sum up this function, it's already not a continuous function in either of its arguments. And so this will cause problems for doing optimization in the way we were doing it. That's not how you spell it, is it? Okay. And so yeah, so this loss function, L, is not continuous, and it causes problems trying to do like gradient descent on this particular loss. Okay, and so what do we do? What we're going to do is, one alternative is just to like, I don't know, try to approximate this loss. And I mean, okay, another thing is like, this is also therefore not continuous, because it's just the sum of these non-continuous functions. And so the domain's not continuous, then the range is also not going to be continuous, and we have all sorts of problems. Okay, and so one way is to like approximate this loss with other losses that make things convex and then suffer some sort of error based on how good your approximation is. And this kind of way of doing things is called using like surrogate losses. So you would approximate a loss with a surrogate that is convex, and then you do all your math on there, and then you have some error between those. And that's one way to do things. But the way we're going to do things is a little bit different. And yeah, the other way is to not do this ERM stuff directly, but go through this MLE business. So in particular, let's suppose we did really want to minimize the 0-1 loss. What would the like Bayes optimal predictor look like? And then if you remember in the regression setting, that was like the expected value of y given x. And then we're like, oh, if we can just calculate this expectation by estimating the conditional PDF, p of y given x, then we can solve the problem. So we're going to do like a similar thing here. So yeah, and now I will start writing. So if you remember f Bayes, the Bayes optimal predictor is just defined as the predictor from the set of all possible functions that minimizes the actual expected loss, the risk, which is the expected value of this loss, right? This loss function. And this is really the 0-1 loss here. And it turns out if you work out this argmin situation over all possible functions, what you will find is that the best choice, or the f base, right? So what's f base? F base is going to be a function from some feature vector x. And what is it going to pick for its label y? Well, it picks what maybe is expected, which is it's just going to look at the PMF of y given x. This is the true PMF of, the actual labels given the feature x. And let's say you had 3 labels here, right? Well, there's some probability given your current feature, which is like, let's say I had some amount of chemicals. Well, then there's some probability it's this wine and this wine and this one. It's going to sum up to 1. It's a PMF. So this takes 3 values for 3 different values of y. And so the question is, which y do you pick? Well, you just pick the one that makes this the largest. So you would just output the argmax y from the label class calligraphic y. So it's just like, out of the 3 different wines, you would pick the one that is the most likely to occur given the current feature. That should be very intuitive, that this is the best you can possibly do. Okay. And this is different than that whole expected value of y given x like it was in the regression setting. But that's all fine. And what we see here is that if we could just somehow, estimate what this PMF is, this conditional PMF, which we were doing before, then we would kind of be done, right? We have some amount of labels. Let's just estimate what this thing is. And then based on our estimate, let's just pick what the most likely label is for a given feature. And so this is going to be this is what the learner is going to look like. The learner is going to estimate this. We're going to do MLE to estimate this. And once it estimates that, it's just going to pick the class that makes this the most likely. Or sorry, it's going to pick the class that has the largest probability. Okay. Is there any questions about that? Because literally after all that's left to do now, it's going to be a little bit more math than before, but it's just to solve the MLE problem. Using the exact same steps as before, but now, and now this thing is not going to be a normal distribution, right? We're going to have to pick something else, some distribution that outputs a finite number of numbers with some probabilities. Okay, let's do that now. So, at this point, you can study this directly where you have just a general number of labels, but it turns out somehow to be easier to break it up first where the number of labels is 2. So it's either 1 or 0. So true or false, or maybe this wine or not this wine, or it is a cat or something else. It is a dog or something else, like these kind of problems. And so for the rest of the class, we're going to study the case where it's a binary classification problem in the sense that the labels are binary. And then it's just all you need to know is what is the probability of one of the labels, and then the probability of the other one's just going to be 1 minus it, right? And so you just pick the one that's the largest. Okay, so let's go ahead and solve this problem using this maximum likelihood formulation we've done before, which is just a procedure, right, to get an estimate of this PMF. Okay. And so I have written a couple things just for the setup, but the way this maximum likelihood stuff, how does it work? Well, we're going to use maximum likelihood to estimate this, right? That's our goal. And the way this procedure works is you assume you've been given some data that's been conveniently sampled in an independent and identically distributed fashion. And if this convenient assumption holds for you, well, then you can go right ahead and work out the rest of the steps. Okay, so okay, so we have this data, each one of these points, and we're just going directly to the case where we're doing machine learning, right? We've already done the MLE basics stuff, whatever. Now we're just going to directly apply it like we have before. And okay, so the question is, what is the distribution, or what is this what is this PMF? If you recall, in the regression setting, the y's were these continuous numbers, and we were like, okay, for some reason, maybe a decent choice is that these are normally distributed. And that maybe made sense. It was like, oh, you had this plot, we had all this data, and then if you look at one x value, maybe there it's like this normal distribution looking thing like that. What's it going to be now? Well, it's actually very You don't lose any generality here because y can only be two numbers. So for each x value, y can only be two numbers. So if I just tell you the probability of both those numbers, that's the whole, that's it. And that's just the Bernoulli distribution, right? So, I mean, I'm going to write it like this, but like this is not an assumption at all, because it's like, it can't be anything other than this, which is that each one of these yi's given some xi vector equal to some particular little xi, well, it has to be Bernoulli distributed, right? And the Bernoulli had a parameter, if you remember, alpha star. Okay. But now the difference here is that for each feature, you could have a different Bernoulli distribution, right? If you have like more of some chemical, well, then the probability of it being this wine might go up now. So really this parameter, just same with the case we had before, it should depend on xi. Okay. And if you remember in the normal distribution case, I guess I'll just write it and then erase it. After we had something like, we had this normal distribution, and we assumed that, oh, the variance was fixed to like 1. And then we said the mu, there's like a mu star parameter that's a function of x. This was the case for regression before. Okay. And then we said we have to pick some function for this parameter that we're going to want to look like. We're going to want to learn this function, right? This is what we're going to want to learn. And if you recall, like, how are we going, like, then we plug it into this whole like likelihood function, and then we're going to try to maximize it, right? We're trying to maximize the likelihood. And then we're going to try to search over all the possible, likelihoods, which is the function over parameters, that will maximize that. But we said, okay, searching over functions is hard unless they're parameterized by some set of weights or something, and then we can search over those weights, right? So then what we did is we said, oh, this mu star, let's give it a specific form. Let's define it as some function that has some weight like weight vectors, that we can then search over those, because every function has a one-to-one correspondence with some weight vector. And so what we chose for this, if you remember, was we said, okay, like let's just say that, I guess I wrote it like this, xi transpose some parameter vector w, right? And there's some true parameter w. So that was really the assumption, that this mean for some reason followed this like linear trend, and then we could make it like a polynomial function if we wanted something more complex. And okay, if you remember a mean, like the expected value of a Gaussian, it could be like any real number, right? So it could be like here, or you could shift the Gaussian to the right. And so it actually made sense to output a number, right? A linear function can output a number between negative to positive infinity. And okay, so now I erase this. And so like the first assumption we might try to do is just reuse this story that we've had before, right? Which is replace alpha star. Oh, not like that. Replace alpha star with just a linear function. And that would just look like this. So you take xi, take its transpose, and then you take the dot product with some weight vector w. And you can do this. It's just a little bit weird, because this quantity can now take numbers between negative and positive infinity, but the Bernoulli parameter can only be 0 to 1, right? That's its range. And so, okay, you can still use this estimate. It's just going to be like terribly off, and you can like clip it and things like this maybe. But hopefully you agree, and we're going to study this. We'll do like a little example at the very end why it's not such a good idea to just use this directly. And hopefully you agree, like intuitively, it makes a lot of sense to just like, somehow apply another function maybe on top of this that squeezes it between the intervals 0 and 1. Right? So that's all I want to do. And I could just clip the function between 0 and 1. But if you clip it, then things are, once again, not continuous, and kind of, well, they'll be continuous, but there'll be these discrete jumps, and you won't be able to take derivatives really nicely. So we're going to just smoothly squish our function into the interval 0 to 1. Right? So like all I want to do is basically take a line and somehow squeeze it such that it becomes something like this between the interval 0 to 1. Okay? And so there is a function that does that. And that function is the following function. So for some input z that takes values, so this z can take, let's say, values between, well, any real number. just like this output could. And then if you apply it through this function, which is just 1 over 1 plus e to the negative z, it will squish it between 0 and 1. And people call this function the sigmoid, or the logistic function. And so we're not going to like this linear function here, and instead we're just going to apply the sigmoid to it. Okay, so we're going to take the sigmoid of the output of this linear function. And now we really do have that this must be an element of 0 to 1. And of course, I forgot the star here, which is that we're assuming that there is some true weight parameter W star that will give us this correct alpha. And this is really where the assumption comes in, is that for some reason this alpha star can be modeled as this function, which of course sometimes it might not be able to be modeled like this, and you might need like a more powerful function inside here. And the way we're going to solve this is by making this like a polynomial type of function inside, which we've seen before, replacing this with these polynomial features. Okay, great. So hopefully that makes complete sense. And once we have that, and we know that this thing is a Bernoulli, we can write out the equation for this thing, which is going to be a function, right, of this parameter, which we plug in this equation for that, and then we just need to optimize over W star. And that would just be some math. So what we will have is that P of y given x for some parameter W, and in this case, yeah, okay, is there's a, remember, I don't know if you remember, I don't know if we saw this before. Well, we have, I don't remember where we saw, at what point we saw it, but there's a closed form equation for the Bernoulli PMF, and it looked like this, which it was like x, okay, to the y. Oh, sorry. It was not x to the y. It was like the parameter alpha star to the y, which is the label, times 1 minus alpha star to the power of 1 minus the label. And we've seen this before. It's like, oh, if this label is 1, well, then the probability of getting 1 is just alpha star. And then this canceled, this goes to, this becomes 1 because you have 1 minus 1 to power 0. And then the other case is the other way around. If you have the label of 0, this term is 1, and then you just end up with 1 minus 0. So 1 minus alpha is the probability of getting 0. We now need to replace alpha star with the corresponding function we chose, right? The corresponding function we chose for that parameter. And that parameter, or that function, was the sigmoid function of x transpose w. And same thing here. And someone online asks a question saying, would this function called the, there's another function called the rectified linear unit. It looks like this. That should be along the x-axis. And this is another function that you can, that takes in a real number and outputs some number for you. But you can see that it, and the question is, will this also work? And you can see it outputs a number that grows much larger than 1. But I mean, it's just a line. And so it squeezes everything down to 0 here, but then it grows like this. And people, I mean, you can technically use this, but it doesn't quite achieve the goal we want, which is to squeeze things between 0 and 1. And yeah, that's all I'll say. For this, for if you just want to do this like simple situation we have here, where you just have this linear function and you want to squeeze it between this, you should be using a sigmoid. Look, yeah, we'll see the ReLU when we get to neural networks. And the ReLU thing will be used inside the neural network, but it won't be used at the very final part, which is the output. Because at the output, you really want to squeeze things or make your outputs in the range you would like them to be. So even there with neural networks, if you want to end up doing like a classification problem, your final, this is called like an activation function, the final one will still usually be a sigmoid, but in the middle things will be ReLUs, and we'll see things like this. Okay. Hopefully that answers that question. But back to where we were, we have this equation now for what py of x for a given param or a given weight vector is. And here there's like some notation and terminology that can get confusing, because I'm trying to, like, there's multiple parameters that I can call parameters, and you can be confused about what parameter am I talking about. And so maybe I'll try to be more careful, which is the random variable y given x. It's described by this Bernoulli distribution that has parameter alpha star, right? That's the parameter of the Bernoulli, the parameter that tells you the probability of getting 1. That's a parameter. But then we've also said, oh, this parameter, we're going to describe it as a function of some other parameters w star. And so for this, I'll try to use the word weights. These are like the weights of your model, which are themselves parameters, but it's the weights of the model that's being used to then estimate this parameter here. But yeah, and this can be confusing because you're trying to estimate alpha star by using this function, which itself has its own weights to do that. Okay. And so yeah, so this is just the equation of the PMF for Bernoulli, and in particular, the actual true function P of y given x, which is the true PMF, is equal to this P of y given x when it's parameterized by, or I should say, when it's based on these weights, W star, which are those true weights. Those ones really give you alpha star. And if you pick some other weights, you might get a different parameter, right? And because you get a different number here. And we're going to try to find the one that makes the likelihood function the largest, the parameter that makes the likelihood the largest, because that somehow tells us that that's the most, that makes the data it's the highest chance that that was the parameter used to generate the data. Okay, so now let's just repeat the math. So yeah, now this part's maybe less interesting from an intuitive perspective. It's just solving some math. Okay, so we want to find W, the weights. We want to estimate, right? We want to estimate this guy here, the true weights of this sigmoid function. And so we're going to do that with MLE. So this WMLE will eventually we'll get to a solution. And right, and the whole hope is that this is approximately equal to this W star thing. And I mean, it will be. Okay. So how does this procedure work? It's exactly as we have seen many times. So we're going to maximize the likelihood function, which looks like this P of all the data given these weights W. Okay. And we're maximizing over these weights. And okay, where are these weights belonging to? Well, they're belonging to R to the D plus 1, right? This is the usual version of things where your feature vector is in RD plus 1, so your weights are also in RD plus 1. And now you can already see this is looking really nice because now we have an optimization problem over some multi-dimensional reals. And we know how to solve these kind of things. All we have to do is just explicitly write out what this likelihood thing is, apply some log tricks, take some derivatives, and let's spend about 30 minutes doing that now. So here we go. First procedure is to remember that the likelihood, well, since the data is IID, nicely we can write down this giant distribution or giant thing over a bunch of samples or data points as the product of them. Okay, so this is using the fact that things are independent. So from I equal 1, and this is the product. Remember, this is product symbol. So you're just taking the product of these type of things, which are the PMFs of xi, yi. These are your data points, and they're the things that are independent. Okay, and then we're just going to do this two steps at once here, which is we take the log of this thing to make it into a sum, and then we're going to take the negative and minimize. So we're going to take the min of the negative of the log of this, and then we're going to apply the log rule and get that we have the sum I equal 1 to n of the log of this, right? Okay, and then we can apply the chain rule on this thing because it's a PMF. Well, technically it's a mixed thing of both of them because x can be this continuous thing, we're going to apply the chain rule to get a conditional and a marginal PMF and PDF. And okay, let's do that. We've done this same thing before. And so we'll get something like this. You get yi conditioned on xi. And now you'd be a little bit sloppy and you put this conditioning on the weights, which is actually like, it should be parameterized by it. And then you have p of xi also as a function of the weights, which we write as a conditioning thing, which was this whole abusive notation where this is not actually a random variable and it usually should be in the subscript, but this is how people like to write it. And then if you remember the log rule, the log of, the product of things, the sum of the logs. So let's just immediately do that. And so you can write this as the plus the log of this thing. Okay. And this whole thing is summed. So far, absolutely nothing has changed since we've done, since we did the case with the regression. It's literally copy and paste from there. Now things are going to change. Well, actually, still nothing is changing because what happens is you just observe that this function has nothing to do with these weights at all. We didn't say what the marginal, how it's based on these parameters. And so that's not going to affect the minimum. It's just a constant being summed. So you can just erase that entirely. So that goes away, still nothing new. And now the new part comes, which is that this thing is no longer a normal distribution, right? Instead, or it's not this normal distribution. Instead, it's going to be the PMF of a Bernoulli. And so that's the new thing, and we plug that in. So we go here, and now we're probably going to need to shrink things to fit. And so this log term is now, I'm just going to copy and paste the equation we have here. And before, this was just the distribution, the normal density, if you remember. Okay, that's the only thing that's changed. And now I remind you of a log property that was, I think, on your midterm, which is the log of a to the b is equal to b times log a. And why is this useful? Well, you can see that, okay, there's a product here which we're going to break up in a second, but maybe let's do that first. So before I tell you about this rule, notice that we're taking the log of the product of two things, and that will now become the sum of logs. Good. And now we're just trying to simplify our math, like the function inside to something as simple as we can get, and then we're going to take derivatives, right? That's all we're trying to do. And we look at this thing inside, and we're like, oh, this is kind of ugly. But lucky us, if you have an exponent in a log, that exponent can come out based on this property. That's the b. And same here, that's going to come out to here. And so let's use that property. And I have to say, it's very nice doing this on an iPad, because I can't imagine doing this on a whiteboard and needing to rewrite every single term every single time. Okay, so we just want to move the y. So you take the log. Let's take this y out. Do this, and put the y here and make it bigger. Okay. And same thing for the 1 minus y. How's that going to look? We're going to move things a bit to the right. Take this 1 minus y, put it here. And there we go. Excellent. So we have ended up with this thing, and it turns out we're not going to simplify any further. This is going to be enough to, we're going to decide to take the derivative at this point. And why did you decide to stop here? Well, it's because in hindsight, you find out that this is a good place to stop. And it's because I let you know that this is the time to stop. Okay. So yeah, so how's this going to work now? We want to minimize this function. What is this function? This function now is going to be given the usual name of like the g of w, where it's based on some weight vector. So it's a big looking function, but we're minimizing over, d-dimensional reals, d plus 1 dimensional reals of this function. All we need to do is take its derivative and set it to 0. Okay. So that's all we need to do. And why are we doing this? Like, why does this make any sense to do this and set it to 0? Well, it's because I'm just going to be an oracle and tell you that things are convex. And this was another reason to have chosen the sigmoid function here, because it turns out this whole thing is still a convex function. And maybe on one of the homeworks you like work out something like this for the one-dimensional case. But you know how this would work. You would just, if things are 1D, you would just take the derivative twice and check that it's always greater than 0. Okay, so but I tell you that things are convex. And now we just need to take the derivative, well, all the partial derivatives of this thing. So let's go ahead and do that, and that will take a little bit of work. So there's a lot of like chain rules that we need to apply here, okay? Because you can see like there's like this thing's kind of a bunch of nested things. Like W is kind of nested deep in the function. Here W is also nested deep inside this thing. But luckily everything's a sum, so you just really need to take the partial derivative of this term and then the partial derivative of this in terms of each dimension. And yeah, to do that, we're just going to define a couple like, terms and then do the chain rule with respect to these. So first thing we notice is, oh, this, this linear thing seems to be appearing in multiple places. So let me give the linear thing a name. This linear function, well, I'm going to give it the name UI. So UI, oh, the thing that I made a mistake throughout here, right, is as soon as I plugged in the PMF, I forgot that these xi's and y's should be indexed with I for the data points, right? So xi, yi, xi, yi. Okay. And yeah, so UI is just xi transpose w, which is going to be this dot product. Just defining all sorts of variables because we're going to want to do these chain rules now for derivatives. And then notice that, well, this quantity is nicely being inside the sigmoid in multiple places. So give that a name, call that VI, which is just going to be the sigmoid applied to UI. Okay. And then I'm going to give this whole quantity over here a name. And trying to make use of every letter of the alphabet now. So HI. Oh, yeah. This is going to be HI of, well, it's a function of what? Well, this thing, we just called that VI, right? So it's going to be a function of VI, and it's going to look like YI log VI. And then I'm going to give this whole thing a name as well. I'm going to call that another letter of the alphabet, RI. And that's just going to be equal to 1 minus YI log of 1 minus, and then I've given this sigmoid thing a name, which is VI. Okay. You can do this all sorts of different ways. Maybe you don't need to define as many terms. And now let's work out the partial derivatives. So we're interested now in taking the partial derivatives of this. So that's going to be terms that look like this, which is the partial derivative of G with respect to each dimension of W, right? So with respect to Wj. J is between 0 to D. Okay, so we take that. And what is that going to look like? Well, that's going to look like minus sum I equal 1 to n. Because remember, the derivative of a sum of things is the same as the sum of the derivatives of the inside terms. So I've already applied that property. Now I just need the partial derivative of this and the partial derivative of this. And in terms of the functions I've defined, that's going to look as follows, which is the first one is going to be, well, it's okay. And now these terms, so the only multivariate term here is the W. So to be completely proper, we use the normal looking D when things are single dimensional, and then curly D, this del thing, for multi-dimensional things. So okay, the correct way to write this is D HI, right? That's this thing is called HI, this whole thing. So I'm going to take the derivative of HI with respect to VI, right? I think, yeah. That makes sense. Vi is this thing in here. So I'm going to just take the derivative of this function with respect to Vi. That's where the W lives, right, inside this Vi. And then I need to take the derivative of Vi with respect to, well, Ui. So then I'm going to do dui. And then I need to take dui with respect to d. And now this is where you should use this del operator wj. That's just the first term. All I've done is I've rewritten del hi with respect to wj, which would have been this partial derivative in terms of a bunch of chain rule steps, like 3 steps. And now we're just going to calculate each one of these 3 and then plug them in. And then for the second term, this r term, we do the same thing. So dri with respect to dvi, and then dvi with respect to dui, and then dui with respect to del wj. And beautifully, this is repeated with this is repeated here, and then these are different. And so we just need to calculate 4 derivatives. So let's do all those, and they're very simple, actually. So dhi with respect to vi is equal to, well, what's the derivative of this with respect to vi? Well, the derivative of log is just 1 over the term inside the log. So it's just yi 1 over ui, right? Oh, vi. And if we plug things in, just to make things simpler for later, because I'm going to plug things in, it's going to look like this. All I've done is plugged in vi. Okay, that's for h. Now for r, ri with respect to vi looks pretty similar. So this is, remember, a constant with respect to vi. Now you have log of this. So the derivative of a log of something is 1 over the inside. And then you have to take the derivative of the inside term, which is just going to be minus 1. Because the derivative of minus vi is just minus 1. So you end up with minus 1 minus yi. And then you get 1 over 1 minus vi. Which, once again, if you plug in the definition of vi, you get minus 1 minus yi over 1 minus sigma of ui. And the reason I haven't plugged in ui yet is because keeping it like this in the final thing will be nice, because there's going to be a bunch of cancellations. So I don't want to, pollute the notation too much yet. Okay, and then 2 more derivatives are left. So then there's the derivative of vi with respect to ui. That's this thing. And then we have to plug in the sigmoid now. Okay, I'm going to save us all some time and just tell you what the result is, which takes maybe it takes a few steps of calculation, because you remember it's a 1 over 1 plus e function, this thing here. So I'm just going to save you some time and tell you that this derivative is equal to, it turns out, the sigmoid of ui, right? So we have the sigmoid of ui. It turns out its derivative is actually the sigmoid of ui times 1 minus the sigmoid of ui. That turns out to be very nice. Okay, so that's an exercise if you want to work out on your own. And then the final one is this partial derivative with respect to wj of ui, which is equal to, well, that's super easy. You look at this. We've done this before. You expand the dot product. There turns out to be d plus 1 sums. And then you look at just the jth sum, right? The one that's multiplying, it's the xij times wj. So then you just get xij. Excellent. And now all that's left is literally just to plug it into here to get that partial derivative. So let's do that. Let's take this term and plug it in. All right. First term, dh, the derivative with respect to vi, that's this thing. I guess this is the easiest way to do it. Put that thing there. Then it's multiplied by vi multiplied by this. Where is that? That's here. Let's take that. Make that a whole lot smaller. That's the next term. And then this is the last term. And that's what we get for that. And then I'm going to make things even smaller so they fit. And then for the r, the next term, this is the first part of it. Okay, there's even a minus already there. Beautiful. minus, and then you take this again, and then you take this again. And then you make it all the same color. And we have our partial derivative. And now if we look at this, we are in luck because this cancels with this, right? They cancel. This cancels with this. So we get a nice simplified expression. Erase those. And then this goes away. And then we are even in more luck because if we try to expand this, I'll just do it all like, if you look at it, this minus with this 1 will give you, okay, maybe let's expand all the terms. This might not be so visually obvious. So all I'm going to do is I'm going to expand this. Okay, so I guess we don't need this everywhere. So expanding the first term, we end up with yi times xi j minus the yi times sigma of xij. Right? Okay. And then for this next term down here, the way we're going to expand this is also expanding this out. Well, I mean, it's the only way to expand it. And what you end up with is minus sigma ui xij. And then the other term is plus yi sigma ui xij. Okay. And now we look at this and we see, oh, this term is the same as this term. And this has a plus and this has a minus, so they cancel. So we're left with, this goes away, this goes away, and we have this. And then even better, there's an xij in both of them. So we can factor that out and move the negative sign inside, and we end up with a very nice looking expression, actually, which is, right, take away the minus. So now it would be like xij is going to be factored out, but I'll keep it to the right for a particular reason. And then I want to write yi minus, but since we applied the negative from the left, it's now going to be sigma of mu I, and now we can plug in mu I, which is xi transpose w minus yi xij. Okay. That's it. So that is our partial derivative of our function we needed to optimize with respect to wj. Beautiful. And now if you squint at this, or well, you don't really need to squint, you just need to remember that in linear regression, when we took or in the MLE thing for the regression setting, when we assume normal distributions and so on, remember we had this normal distribution and then we applied all these steps, and then we also had some function at the end, and then we took its derivatives and so on. And you might remember the function we got there, I'll write it for you, is the following function. For the partial derivative. So the only difference was the sigmoid here. And even better is if you called this thing somehow well, this is like our parameter. Remember, this was our function of the parameter. And this was also our function of the parameter mu star. And so this is not necessary to know, but it turns out that, this is obviously not for a star. So this is our function we chose for the parameter, and this is the function we chose for the mu parameter. And it turns out that these, like Bernoulli distribution and the normal distribution, and there's more, there's like the Poisson and the gamma and stuff, these all are part of this like when you make the parameter assumptions in this kind of special way, they're all part of this called like, well, all these distributions are from this thing called an exponential family. And then when you make these kind of assumptions for the parameters, it's called doing this like generalized linear modeling. And it turns out that for all of these distributions, and if you make these type of assumptions for their parameters, you always end up with an equation for their partial derivatives of this form, where the term here is always the expression you chose for their parameters. And you don't need to know this. This is, I guess you learned this in 467. But you can see that this is just a more general pattern that emerges. And so then you don't need to do these partial derivatives every single time. And you don't need to do all these steps. You would just know that that's always going to be the case. But for this course, we did work things out like this. And OK, so that was besides the point. We finally got to our objective, which is taking these derivatives. And now we need to set this to 0. And the question is, can we do this? Can we solve for it? And actually, it turns out that this is a particular case where there is no closed form solution. And so now we can't just set it to 0, right? Instead, we're going to need to actually use gradient descent to optimize. And we already know how that works. So that's just going to say that, well, the whole W vector at time step t plus 1, no closed form solution. Closed form solution. And so to the rescue, we have gradient descent. And I literally just write for you the update. This is just a copy and paste from what we already know, is that at the t plus 1th step, you take the old parameter weight vector, you take the old weight vector, and you take steps in the negative gradient direction that are multiplied by some step size of the gradient of g of wt. And recall the gradient is just this vector of all the partial derivatives, written out from j equal to 0 until d plus 1, or sorry, until d. And maybe I can even write this at the end here. This j, remember, is from 0, 1 up to d. That's all the indices of our weight vector. Okay, so we just need to take these gradient steps. We know what the gradient is. Well, we know these partial derivatives, and it turns out, if you remember, if you write these out all as one vector, you then notice that the only thing that j is changing is xij. And so then this is just a constant that can get factored out of every term in those partial derivatives, and you end up with the gradient just being, well, xi vector multiplied by this constant. So in particular, this gradient, we've done this as well before, which is, because it's exactly the same equation now as before, except now you have this sigmoid here, is just equal to this expression that we just solved for. I guess we do not need these big brackets anymore, with xi replaced with xi vector. Nice. And yeah, and of course, this is a element of Rd plus 1. Vector in Rd plus 1 multiplied by a big constant. Well, okay. Yeah. Yeah, nice. So that's what we got to. And then if you make like if you do this for some number of epochs, right, you're going to arrive at like a Wt, where t is the number of epochs you've been running for. And if you make t large enough and you choose a good enough step size, you're approximately going to get to W MLE, which is the actual MLE solution, right? That's what we just did. All we've done right now is after all these steps, what we have come to is the gradient descent giving us hopefully something that gets closer and closer to what this actually is. And the reason we wanted this was because we wanted W star. And the reason we wanted W star was because we wanted this parameter, which tells us the probability of getting some label being 1 or 0. And the reason we wanted a label being 1 or 0 is because our final predictor, right, is going to be the one that just takes the label that has the largest probability. It's this argmax thing. So let's write that now. We are finally ready to define our learner, right? which is just basically unwinding this whole procedure backwards now. So yeah, I'm just going to give this a name at the end. So like at the end, this is what we wanted, right? Which was like alpha star of some x. And what we say is that this thing is approximately equal to, right? Well, first of all, we know it's exactly equal to, this was our assumption, that this was exactly equal to the sigmoid of x transpose w star, which of course is then approximately equal to our estimate of this using WMLE. And then there's some error because we're doing gradient descent as well. And I'm going to, for reasons we'll see later, I'm going to call this some function. It's going to be our MLE function. That is just this thing, well, what is it? It's a function of x, right? What is our function of x? FMLE. Okay. So now let's see how our learner looks. So at the end of the day, we want a learner that's going to take in some data set. And it's going to output some f hat. And I'll give this f hat the name f hat for binary classification. And then we'll see that the multi-class one maybe is a different, slightly different. Okay. So, and then how is this going to work? So let's get to the definition of f hat. So the way this is going to work is we're just going to start from where we wanted, which is we just wanted to calculate f bays. That was really our goal. And okay, this is what we wanted. And to get f bays, we needed this guy. We just needed to get this PMF, this conditional PMF. We just knew the probability of the label. We would just pick the one that's the most like the highest probability one. And now, okay, well, let's write one more step. And then we assume that, oh, this function actually, it's a, well, it's a Bernoulli, and then it depends on this parameter like alpha star, but then alpha star itself depends on another weight vector W star. So we write it like this. It depends on this parameter W, or this weight vector W star. This is the true one, and the assumption was that these are indeed equal. And now we have an estimate of W star, so we're just going to plug in MLE and say this is an estimate of this whole procedure here. Okay. And yeah, and that there, what do we have here? We have a function that takes in as input x, right? Or what do we have here? We have here a function that takes in x, and then if we calculate WMLE, which we know how to do it from above, we plug it in here. We can then just take the argmax. We of course know the number of labels there are. Like this is something you're told, and then you can output it. So this turns out to be exactly what this binary classification predictor we output is going to be. So what's the procedure? The procedure is output this thing. Well, what does that mean? It really means calculate this thing, and then take the largest, the class with the largest, or the label with the largest probability. So all that's left is calculate this thing. And then to calculate this thing, well, that just means calculate WMLE, and then plug in WMLE into this equation, right? So that equation, if you recall, is this thing. So once you calculate WMLE, you plug it into here. That gives you the probability, right, of that y given that x. And then you do that for both y's, for y equal 1, y equals 0, and then you just pick the one with the largest probability. Okay. That's the learner. But maybe that's a little bit uninterpretable. So there's all sorts of other ways to write this now based on those equations. So let's just do that. So we can look at what is this when y equals, okay, well, technically we could just plug in the equation, remember, which was that product thing, which kind of looked ugly. And maybe I'll bring it down here and this is one option. You just take this and plug in WMLE. And that is what you're taking the argmax over, right? But since y can only be two things, it's a lot nicer to just break it up into the two cases. So either it's this or this, right? When y was 1, this is the case where y is 1. And this is the case when y is 0. So let's just write it into two conditions. Okay. And so what's this? So this thing here when you plug in MLE, and I'll make this in blue, because right now all I'm doing, like the blue stuff should be stuff that's like, extra thinking going on in the background, then we come back to where we were. So this stuff, well, this is just, what is this? This is the probability that y equals 1, right? That y equals 1 given x based on WMLE. So hopefully that makes sense. Like once we have WMLE, the probability of the class being class 1, label 1 is just this. That's all you would calculate. And the opposite thing says that the probability of y equaling 0, well, it's just 1 minus this thing, right? Which is exactly this term over there. Okay. That's what that tells us. Great. So why is this useful? Well, now, and okay, I don't know if it's, for some reason I called this thing FMLE. I don't actually recall exactly why this was so important, but let's just give it this name as well for now. So this FMLE thing basically, oh yeah, this FMLE thing just outputs the probability of getting the class 1. This thing is just the probability of getting class 1. And now we can look at when exactly is this, well, okay. Now we look at this argmax thing, right? Which is, so this thing can be, like, there's only 2 values of y here. So you're taking argmax over 2 things. And you know that those 2 things sum up to 1 because the probability of 1 plus this thing needs to sum to 1. So in other words, when are you going to pick class 1? Well, you're going to pick class 1 when the probability of being 1 is greater than 0.5, right? So that's another way of thinking about it, is like this. So now we're going back to this binary. This is the predictor, your learner outputs. What's it going to do? Well, it's going to output the class 1, right? When is it going to do that? It's going to output it if this quantity here, right, which is just the probability of getting 1 that you calculated here. It's your estimate of the probability of getting 1. Well, if the probability of getting the first class is greater than 0.5, and then alternatively it's 0, well, if the probability is less than 0.5, or the probability of getting 0 is greater than 0.5, but we'll write it like this. The probability of getting 1 is strictly, let's say, less than 0.5. That should make complete and intuitive sense for the binary case. And if you look further at the way the sigmoid works, right, this is a sigmoid function. Let's just visually look at it. That's all you need to see. You see that exactly at 0.5, sorry, the point at this, it takes the value 0.5 at exactly 0, right? So when it takes as input 0 here, it's a value of 0.5. And remember, what is this? This is our probability of getting 1. So as soon as its input z is slightly above 0, then it's greater than 0.5. And if it's below 0, then it's less than 0.5. So in other words, you can also think of this as not when the sigmoid is greater than 0.5, but you can just think of when the linear function inside is greater than 0, or when the linear function inside is less than 0 for the other case. Okay, so there's all of these equivalent ways, and why this is also useful is because when you look at it in this view, you can then plot it and it has a nice interpretation. Okay, so in particular, the point where this equals 0 is somehow the point at which you transition from predicting 0 to 1, or the other case, right? So basically, you can think of it as there's like a boundary. There's the boundary where somehow all the values, right, of x that satisfy the case where they equal to 0, this is like the cutoff point. And then anything past that boundary is going to be either 1 or 0, and then the other way around for the other one. So visually, it should be something like this, which is that if there was 2 dimensions of x, I can draw some boundary like this, and it turns out to be a linear one because of the choice of x transpose w, such that, and what is this boundary, right? This boundary here is the case where x, where this is the x vector, right? This x1 comma x2 thing is equal to, oh, not x, x transpose w is equal to 0. That's the line. And yeah, and then so if you're to one side, you end up predicting all zeros, and then the other side, you end up predicting 1. And this might be a data set you have, and your solution might end up being something like this, which is the way to interpret this binary classifier that you end up getting is you take in this data, you then produce the binary classifier. The way it works is really you end up with this like decision boundary that you can draw, and anything on this side will be, let's say, 0, and on this side will be 1. Okay. And for the 2D case, it's very easy to see how this works, right? So I guess I already said this, but you end up with this x transpose w, right? Equal to 0. And this w should be like your solution, like WMLE. And in the 2D case, this is really just x1. Oh, sorry. It's like, okay, so it's x0 times w0 plus x1 times w1 plus x2 times w2 equal to 0. Okay. And x0 is 1, so that's just that. And then if you rearrange this thing so that you can plot it on this plot on the plot we have here, I would like to plot x2, right? That's going to be kind of like my y-axis, as a function of x1. And so if I rearrange it, I get that x2 equals to minus x1 w1 over w2 w0 w2. And it turns out this is just an equation of a line, and that would be exactly this line. Okay. Great. And so, yeah, and other things is like this x transpose w is on this side. What is it? Well, if you're predicting 0, what must be the case? Well, it must be the case that this is less than 0. And if you're predicting 1 over here, it must be the case that this is greater than 0. And in other words, that means your predictor, your binary thing that we've outputted, here is equal to 0 for these x points on this side. Because, right, it's equal to 0 whenever this is true, and the opposite on the left-hand side. Okay, and so in general, actually, this like equation that we had, which was x transpose w equal to 0, well, this, if you just know, I guess, some linear algebra, this is just, so if we are in d dimensions, this is a d minus 1 dimensional. And so it's a d minus 1 dimensional plane, but in higher dimensions, people call it a hyperplane. And so if d equals 2, then a d minus 1 dimensional plane is a line. D equals 2, so the d minus 1, so we have a one-dimensional hyperplane, which is a line. This is our plane. In 3 dimensions, you would have like a two-dimensional hyperplane, which is just a normal plane. Okay, that's what I have to say there. And it turns out that for all of this stuff, you can do polynomial features. So polynomial features apply like before in exactly the same way. You just replace these x transposes with, you know, the phi map of x. And you can also, instead of doing MLE, you can do map. And map gives regularization just like before as well. So you end up with some sort of objective here, this is g of w, that also has an extra term for this regularization, this prior. If you remember, there would be like an extra plus lambda type of thing going on. Okay. Great. Okay, so you have your binary classifier. And you may have heard a name before of people calling this whole thing logistic regression. Okay. And so logistic, okay, maybe makes some sense. That sigmoid function, we called that the logistic function and so on. But what is going on with this regression business? We're doing classification. And people say that like to solve classification, or like one possible learner is the logistic regression learner. It's like, where is the regression going on here? And it turns out that you can view this whole procedure as solving a regression problem, which I will tell you what it is in a moment, but maybe you've already figured it out, and then making use of that solution to then classify things. Okay. What do I mean by that? Well, let's look at the learner. What is the learner doing? The learner outputs this function. And what is this function? Well, it's the argmax of this thing here. So all I needed to do was solve for this, right? And solving for this, well, okay, maybe I can treat the solving for this as a, well, like first of all, this thing can take values, right? This is like a probability of 1 or 0. And in particular, if I solve for the probability of y equals 1, right, then I immediately get the solution for y equals 0. So really all I need to do is solve what is the probability that y equals 1. And what's that probability? Well, that's a continuous number between 0 and 1. So in other words, I can think of this as a regression problem where all I'm trying to do is from data, get a predictor that predicts the probability of getting 1. Okay, and that's just a number between 0 and 1. And so you can think of this whole thing as solving the regression problem using the logistic function. And so your function class is going to be the set of logistic functions, the sigmoids, and that's what we were using. With some loss, the loss we will see, it's just going to be the one we've actually encountered just now. And then on top of this logistic regression thing, you have to take this argmax thing. And so logistic regression would just be the procedure to solve for this using regression, which we've actually, turns out we're gonna see right now that what we just did is equivalent to a regression problem with some loss. And then after that, you apply this thing. So when people say logistic regression, they really mean solve this, and then somehow there's this implicit knowledge that, oh, you're also going to take the argmax after you calculate your probabilities, which is not really part of the regression problem, but it's part of how you're going to predict afterwards. Okay, so how do we map this to a regression problem? Well, the way this mapping is going to work is now we're going to talk about, like, for the logistic regression case, we're going to have labels that are numbers between 0 or 1. So that's going to be kind of like our label class. So it's going to be numbers between 0 and 1. So these are the labels for the logistic regression problem, numbers between 0 and 1. And what is this? This represents, what are these labels representing? They're not representing the classes anymore. They're representing the probability that the original label y was equal to 1. Given some feature x, which was, if you remember this alpha star thing. Oops. I just want this one number. Give me that one number, we're done, right? We already know how to solve. So that's what I want. So I'm just trying, and this number is between 0 and 1. So I just want to solve that regression problem. Okay, I've already, like, how do I solve that regression, or how do I calculate this? Let's look at it. If I want to do regression, I need somehow like a loss to minimize, right? Ultimately, okay, let's see what the learner will be like, and then we'll fill in what the loss and stuff need to be, just based on what we've already done. So my learner is going to be like this. It's going to take in a data set. It's going to output an f hat. We've seen this a bunch of times, and I'm going to run ERM, right? I'm going to minimize the empirical risk. So what's f hat going to be? Well, f hat is going to be the argmin f in some function class. We'll define the function class soon, such that the empirical risk is small. Right? Okay. Now all that I need to do is somehow pick a reasonable choice for a loss function or empirical risk here and function class such that I get some reasonable solution for this. Okay. And so let's just write out the definition of this one time with the loss in there. So what does this look like? So this looks like 1 over n sum I equal to 1 to n of some loss of f of xi, yi. And so I'm left to choose some loss. Okay, I can pick anything I want here. And I can pick any function class I want here. And then I'll get some solution, as long as I can, optimize and so on. What's a good choice? Well, maybe I shouldn't say what's a good choice, but like, I can tell you a choice which we already know the solution to. Here's the choice. So let's just visually remember this. I want something like this. I want to minimize some sum of things, Remember, we already had a sum of things. So probably that thing in there, I'm going to pick the thing we had before. And then I'm going to minimize over some function class. And I better match the function class we've been using before. So let's just go up to, where did we see something like this? Maybe here, right? So I'm minimizing over something, like it's a sum of things, right? Okay, maybe I'll move the minus inside. And this is going to be apparently my loss. Okay, and so what's the function going to be? Well, maybe this thing is my function. So let's see if how that's going to work, and that is going to work after all. Otherwise, I wouldn't be telling you this. And so, just to be very clear, what I'm saying is that if you choose the loss to be of this form, where your predictor of f is of this form, parameterized by this w, you will actually end up solving this will be exactly the same as solving the ERM problem with that particular loss in that function class. So that's going to be the last thing to end the class, is I just copied that. So that's going to be my loss. Okay. So this is going to be my loss of f of x, y. But there's no f of x here. And these yi's are no longer i's. And these, okay. So what is my f of x? Well, I'm going to call this sigmoid x transpose w thing the f of x. So that's my predictor now. So supposedly my predictor is going to have this form. Right? And for that reason, if I want that to be the form of my predictor, so that then when I plug it in and do the optimization, everything looks like we've already been doing, what I should do is then pick my function class to be that, right? I should pick my function class to be all f's that map from x to y. And y here is this, let me make it very clear. It's 0 to 1. These are probabilities that we're mapping to, such that f has this form, and w is, of course, some vector in Rd plus 1. And if I did this, then I just directly plug it into here, and I find out that I have and there's one last thing, which is the minus will be moved into here, and I will get minus, let's just make it very clear. You will get minus this whole thing. And then if you look back up, it looks exactly like that G solution. So in particular, this will be equivalent now to solving the argmin parameter or weight vector in Rd plus 1 of the G function we saw earlier, of G of W. Good. And that is just FMLE. Okay. So that's how this logistic regression maps. And next class, we'll talk about multi-class classification and see how the story goes there. Okay, well, have a good weekend, everyone.